So lastly, we come to a very important propagator. This is known as the Feynman propagator. And this plays a central role in quantum field theory, as we shall see in the coming weeks. So what is a Feynman propagator? It's a propagator like any other propagator, but it has its own specific boundary conditions. So the definition of the Feynman propagator for bosonic operators is the following. The Feynman propagator d of f x minus y is given by, so it's defined to be the theta function x0 minus y0, the vacuum expectation value of phi x and phi y, plus the theta function of y0 minus x0, and the vacuum expectation value of phi of y, phi of x. Now this is also written as the vacuum expectation value of the time ordering operator of phi x and phi y. So what is T? T is the time ordering operator. So T is known as the time ordering operator, and it plays an important role in quantum field theory. And so T acting on two operators, say phi 1 at x1 and phi 2 at x2, will order them according to their time argument. So if x1 0 is greater than y1 0, sorry, x2 0, then the time ordering operator will order them in this way. So the earlier operator is on the right of the later operator. However, if x1 0 is less than x2 0, then the time ordering operator will put x2 first and x1 after that. So this is if x2 0 is greater than x1 0. So this is the time ordering operator, and as we can see, we have chosen the theta function such that this is time ordered. You can show that the Feynman propagator with this boundary conditions is given by d of f x minus y, and in the limit where epsilon is a positive quantity which goes to 0 from the positive side, and d4 of x divided by 2 to the power 4, 2 pi to the power 4, I times e to the power minus I k x minus y divided by k squared minus m squared plus I epsilon. So the I epsilon prescription is very important. It's known as the Feynman prescription. And what it is telling me is that the pole structure of the propagator should be such that this thing should be pushed up a little bit, and this thing should be pushed down a little bit, so that when we do this integral, when we do the contour integral, and we go along the x-axis, it's clear, which pole that we have to include in which integral. So again, you can show that for, as in the previous case, for x0 greater than y0, we have to close the contour on the lower half plane, and for x0 less than y0, we have to close the contour on the upper half plane. So the Feynman propagator is a propagator which is non-zero both for x0 greater than y0 and x0 less than y0. So it is both a retarded and an advanced propagator. And we shall see that the fact that it is non-zero in the past light cone as well as the future light cone has important physical interpretation. We shall see that one will have an interpretation of a particle, the other one will have an interpretation as an antiparticle. But this is where we end today. So anyway, let me just end with a few comments. It's convenient to express the boundary condition of, say, a propagator like this as a contour integral. And the contour was chosen in such a way that this was a retarded propagator. And the other thing is that the Feynman propagator was non-zero for both choices of contours.